A 7-fold won't fit, and any number higher than that you can try with and you won't get it to fit either. And so this is the reason why we only see 4 different orders of rotation symmetry within any crystal form. Okay, so the second operation, and remember I'm talking about plane groups here now, so the second operation is that we can have mirror, bilateral symmetry or reflection symmetry, depending on what you prefer to call it. And so this basically means that we have a plane or a line through the centre of the object, and any point perpendicular to and equidistant from this line is identical. So taking these images down the bottom here, the yellow dashed lines represent the reflection lines within these symmetric structures. Okay, and the third possibility that we encounter in 2D plane groups is something called a glide reflection. And basically what a glide reflection is a combination of 2 types of symmetry. It's a combination of translation symmetry and a combination of reflection symmetry. And it's shown in this pattern here. And so what we have with a glide symmetry is where we get translation by half of the unit cell combined with the reflection about the axis of translation. So if we start with this molecule here and we translated half a unit cell along the red axis, and then we mirror this molecule about the red axis, then we come up with this structure here. And so that therefore is indistinguishable from the original orientation. So that's what we call a glide plane or a glide reflection. Okay, so by combining these 3 different types of symmetry, taking into account that all crystals have translation symmetry, and so these are not considered in enunciating in crystal space groups. We have rotation symmetry of 4 orders, we have mirror symmetry, and we have glide symmetry. And we therefore come up with the 17 2D plane groups, which are possible to describe 2D projection images of untilted specimens. And so these are listed on the left-hand side here. The unit cell geometry is shown in the second column, the highest order of rotation, the point group that these therefore belong to, which takes into account the rotation order as well as any mirror planes, and then whether or not we have a glide plane in this particular plane group. Okay, so just going back to one of the earlier slides where I mentioned briefly the difference between the 17 2D plane groups and the 17 2D space groups. So those 2D plane groups describe projection maps of untilted images. The 17 2D space groups describe the space group of the actual 2D crystal itself. And so fortunately for us, the fact that there are 17 of each is no coincidence. These two terminologies actually map somewhat trivially to one another. And that's shown in this next few slides here. So basically we've got a couple of extra operations which are possible within 2D crystals, 2D space groups that aren't possible within 2D plane groups. And one of these is if we have what's called an in-plane centre of rotation. So if you consider that you have your molecules all arrayed within one layer, and then we have either subunits or differently arranged molecules within the unit cell which are oriented up and down. This would be an in-plane centre of rotation. So we have a rotation axis which relates to adjacent molecules, which is not actually penetrating the plane that the beam penetrates. Okay, so I'll show that in the image. Basically what it means is that we have a rotation plane centered either in the XZ or the YZ plane and not in the XY plane, which is the viewing plane. Okay, now, as I said, a lot of these space groups map trivially to the plane groups, which I mentioned earlier. And in the case of the 2-fold in-plane centre of rotation, this actually maps somewhat trivially to a mirror plane in 2D projection space. And the reason is shown by this image here. So if we consider our chiral molecule, shown on the left here, and then we apply 2-fold in-plane rotation to this, what we get is basically the upside-down version of this molecule. If we then consider the viewing plane, where the eye is here, and look at what this would look like in projection space, what you can see is that the molecule on the left looks like this, the rotated molecule on the right looks like this, and you can see that there's actually a mirror plane taking the place of the 2-fold centre of rotation, which relates these two images. And so this is how we get mirror symmetry within a projection image. It's actually an in-plane rotation. Okay, so to take that a step further, I've said that a mirror plane is equivalent to a rotation. So this means that in the case of a glide, we have translation effectively followed by an in-plane rotation when we translate this to a 2D space group. And what this symmetry operation is called a screw axis, which is a term that many of you may have heard before. Basically, a screw axis involves translation by 1/n of a unit cell combined with the rotation of 360 degrees about the axis of translation, 360 degrees divided by n. Okay, so for example, a 2-1 screw axis is equivalent to translation by half a unit cell and then rotation by 180 degrees. And so this pattern here shows a 2-1 screw axis. So you can see the unit cell here. When we translate by half a unit cell and then rotate by 180 degrees, we come up again with an object that's indistinguishable from the original. In fact, the 2-1 screw axis is the most common and, to my knowledge, the only screw axis which appears in 2D crystals. Yeah, Tom?
So that I don't quite understand. If this is the unit cell, then you just translate. So the unit cell would be one of the cylinders to get a screw axis in there.
Yeah, okay, so this is a simplified diagram, so maybe we have some sort of asymmetry in this cylinder. Yeah.
But then you just translate it by one unit cell. There's no screw axis.
Yeah, okay, so, alright. So if we were to build this up so this is one line out of a crystal. If we were to build this up in a dimension coming out of the screen, where we had this offset, then and introduce some sort of asymmetry into this cylinder, then we would introduce a screw axis. This is a simplified diagram basically. We would need to introduce asymmetry into one of these units in order to introduce a screw axis. Does that make sense at all? I've got some actual crystal examples in future slides, which will probably highlight this better. This is just a schematic drawing, so maybe I'll just move on to those and highlight it there. Okay, so given that the mirror plane is equivalent to an in-plane twofold, and that a glide symmetry maps to a 2-1 screw axis, then what we can then do is take these plane group notations here, translate them to the corresponding 2D space group of the 2D crystal. And so you can see on the right-hand column here, these are the space groups which are probably more commonly quoted in papers, particularly those that deal with 3D reconstructions, which many of you may have seen before. Okay, so just to, for anyone that's not familiar with this plane group notation, how it comes about, basically we have a four character notation which describes each plane group. And so what these characters actually mean, you have either a P or a C that starts off this notation. The P refers to a primitive cell, the C refers to a centered cell for short, or a face-centered cell. The second number within here is basically indicating the highest order of rotation symmetry within our molecule. If this is absent, it usually means that the rotation symmetry is 1. If it's a 2, a 4, or a 6, or a 3, it indicates the highest order of rotation symmetry. We then have two letters which indicate the position of mirrors or glides. And so the first letter here indicates the position of a mirror or a glide plane relative to the main translation axis of the pattern. Okay, so this is axis A, a vector A, which describes our lattice vector A. And then moving on to the last letter, this basically describes a second glide symmetry, which results from 180 degrees divided by the height, which is positioned 180 degrees divided by the highest order of rotation symmetry relative to the first. Okay, and so basically taking that into account, the knowledge of all of those plane groups, we come up with 17 plane group definitions which describe all of the possible symmetries within a 2D projection image of a 2D crystal. Alright, so now I just want to go through a few concepts in a little bit more detail and just touch on some considerations for symmetrical averaging of data and identifying symmetry within your images. So first of all, I mentioned 2 slides back the difference between primitive and centered cells. So for anyone that's not familiar with the difference between these, this slide should highlight it quite well. So basically, 15 of the 17 plane groups are described by primitive cells, and the remaining 2 are described by centered cells. And what this means is a primitive cell is basically the minimal region repeated by lattice translations representing the unit cell. A centered cell has what's called internal repetition, and so if we consider these points within a crystal matrix in this image here, and if we were to draw a primitive cell, for example, this green cell here would represent a primitive cell, whereby we've got one net copy of the unit cell represented within the primitive cell. So each one of these dots represents a copy of the unit cell, and you can see we've got roughly a quarter of the unit cell represented in each corner. So this is a primitive cell that only contains one net copy of the unit cell. The second cell that I'm going to show here, however, is a centered cell because it actually contains 2 net copies of the unit cell. And so you can see we've got one full copy in the middle, and we've got one quarter copy again at each corner of the unit cell. So this contains internal repetition, contains all of the information described in the unit cell in 2 copies, and so this is why we call it a centered cell. Okay, so this is a structure that some of you would have seen last night. Bernard Kulbrand presented it. It's the HOMG structure, and the reason I chose this is I found it quite interesting because it was within the one paper we had presented 2 different crystal forms of the same protein, one of which was a primitive cell and one of which is a centered cell, and so it highlights quite nicely the difference between the 2. So the one on the left is a primitive cell, the one on the right is the centered cell, and so you can see that concept I just illustrated with points on the crystal lattice. The minimum repeating unit, which is required to translate this motif over the whole crystal, is shown enclosed in the green boundary here, and so we can shift this up, right, left, to come up to repeat the pattern basically. And so this contains one net copy of the unit cell, which can be translated in any direction to come up with the full 2D crystal. So this is a primitive cell. On the right, however, and circled in red, you can see that by taking this small repeating motif here, we can shift it to superimpose on here, on here, on here, or on here. And so within this unit cell, defined by the black square, we've actually got more than one copy. We've got 2 copies of this minimum repeating motif, and so that's what makes this a centered cell. Now, why would we do this? Why would we choose a centered cell and not a primitive cell? And the answer is basically that usually a centered cell buys you more symmetry than a primitive cell. And so remembering that symmetry is a form of averaging, and averaging is what improves our structure and gives us higher resolution. So shown in green here is the centered cell that was chosen to describe this crystal. We could describe this by a P1 primitive cell, and that's shown in red here. However, this P1 primitive cell has basically no symmetry. It has translation symmetry, and that is all. The CM cell, the centered cell, has a mirror plane that goes through the center, and so we basically increased our symmetry by 2-fold. That's why we describe it by a centered cell. Okay, so now I come to the examples which I mentioned earlier. So I'm going to show you some examples in real space and some examples in Fourier space. Yes?
So you increase the symmetry by 2, but you reduce the number of unit cells by 2. So what's the net gain?
That's a good point, actually. So you reduce the number of unit cells by 2, but with symmetry you're averaging. Okay, let's think about this.
Can you go back on that?
Yeah, sure.
I think the net result is the same. I think it's a decision that I made early on how you describe a crystal. And also that a lot of crystals start when they learn about us, they came from diffraction patterns rather than start off with learning about their diffraction pattern rather than in the real space. So maybe at that time that because the systematic absence and things like that, that makes it more sense to describe them as differently. So you group your diffraction pattern separately in the 2 different cases. It's just my guess. I just know that normally when you make a choice, you choose the ones that has the highest symmetry. It's a sort of a convention that's been decided at a certain point.
Yeah.
Well, it's actually the point where you average. If you choose a higher symmetry, then you average earlier. Let's say in the diffraction processing, you fuse together your very high noisy amplitudes that you integrate, and then you get a better signal to noise, as opposed to going at the very last possible moment where you have a lot of unit cells. So you might just be better off processing and getting a better signal earlier on.
Just to add to that, I mean, really there's only a certain kind of fundamental amount of repetition in any image, and as soon as you find the smallest repeating unit, which is going to be the one on the right, you basically squeezed everything there is to get out of it, and that's going to be
Okay, so we'll move forward. Okay, so this is a real space projection map of an RC47 crystal. And so this projection map had, this unit cell has symmetry P2GG, or in 2D space it has P22121. Okay, so this means that basically the projection map has 2-fold rotational symmetry and it contains 2 glide axes. And these are shown, the centers of rotation are shown by the pink diamonds, and the glide axes are shown by convention by dotted lines. Okay, so I've just got some movies which actually show in real space that by applying these symmetry operations, you can see that the resulting shift in the unit cell generates something which superimposes and is indistinguishable from the original. So this is the 2-fold center of rotation, and you can see that the superimposition at the start and the end of the animation is pretty much perfect. Okay, so, and this is one of the glide planes, so basically we get translation by half a unit cell and then reflection about that glide plane. And then the second glide plane goes in orthogonal to the first, and again you can see the translation and then reflection generates something which superimposes perfectly. Okay, so that's our real space example, but one of the interesting things about symmetry is that any symmetry which holds in real space also holds in Fourier space, and so this is the way that programs such as Allspace use our Fourier transform of our crystal or our diffraction pattern of our crystal from electron diffraction to work out the symmetry that describes the unit cell of our crystal. Okay, so this is a Fourier transform of a crystal image from aquaporin 1 solved by Aleph Mitra, and the reason that I chose this particular diffraction pattern is because it was one of the few papers where I could actually find a real space image, a diffraction pattern, and all of the amplitude and phase data contained within the paper. And so that was pretty handy for the purpose of demonstration. So we have our diffraction spots here, our Fourier transform, and we have the A and the B axes, reciprocal axes of our crystal. And so just to go through a few things with respect to this Fourier transform and what it actually tells us about the unit cell, the symmetry of the unit cell and the crystal. So first of all, we can see that the length of A star and B star is roughly the same, and we can also see that the angle separating them is approximately 90 degrees. So what this tells us instantly is that the unit cell of our crystal is a square unit cell. And so if you go back to that table which I showed earlier, it listed a number of unit cells which had a square geometry. So we're dealing with one of the unit cells that has that square geometry. Okay. The second thing, if we examine all the phases, and I've just shown a few of them here, we can see that all the phases within this Fourier transform, and the phases being the second number shown in the parentheses, have either a phase of 0 or 180 degrees. And so what this means is that the space group is centrosymmetric. Effectively, this means that the unit cell has twofold symmetry, and I'll come back to centrosymmetry in the next couple of slides. Okay, so we know that it has twofold symmetry because it satisfies the centrosymmetric requirement. If we look for further symmetry, we can see that points related by rotation through 90 degrees also have equivalent phases, and there's one example shown here. We've got a phase of 179 and 178, so these are approximately equivalent, and if we look at a number of other points that are related by 90 degrees, we find the same thing. So this means that the highest order of rotation symmetry present within this Fourier transform, and therefore present within our unit cell, is P4. Okay, some of you may have noticed that there's some reflections missing from this image, and in particular the odd reflections along the A star and the B star axes. And so what this means, in conjunction with the fact that a few spots have particular phase correlations, is that we have a glide symmetry present. So just to go further with that, the spots equidistant from the A star vector are out of phase by 180 degrees. And you can see this in the red spots shown here, where we have 180 and 0 for these equidistant from A star, and also in the blue one shown further down, we've got 175 and 2. So these two spots are related by reflection symmetry about the A star axis, as are these. There's also missing spots along the A star axis, and this basically is the hallmark of glide symmetry within our unit cell.
Yeah, just to make a point there, for the phases, this is only going to be the case if you're actually on a symmetry center.
If it's shifted to the correct phase.
Right, exactly.
Yeah. Okay, so what happens when we pull all this data together basically is that we can identify that the unit cell that we're dealing with in this case has symmetry P4GM or P4212. Okay, so basically this space group is defined by the characteristics that it has fourfold rotation symmetry, and the fourfold centers are shown as green squares. It has one pair of glide axes and it has one pair of mirror lines. And these are all properties that we can basically draw out of the information that's contained within the Fourier transform. And so by doing some phase comparison based on all of the data contained within our Fourier transform, we can basically determine what the space group of our unit cell is. Okay, so just a couple of points which I said I'd come back to. One of those is the centrosymmetric condition. So basically any unit cell which has twofold symmetry has this centrosymmetric requirement. And what that means is that all space groups with inherent twofold symmetry must have phases universally equal to or approximating to 0 or 180 degrees. The reason for this is, as I mentioned earlier, Fourier transforms must have the same symmetry as the unit cell which they describe. If we consider here some sine curves which are shown here with particular phase shifts, you can see that where we have a phase shift of 0 or a phase shift of 180, then we have symmetry about the origin of the Fourier transform. If we take, for example, a phase shift of 90 or any other phase shift, in fact, we don't get symmetry about the origin, and therefore the centrosymmetric requirement is not met. And so this is the reason why twofold symmetric space groups always have 0 or 180 degree transitions, phases rather. This is beneficial because basically when we're processing our amplitude and phase data, we know that if there's twofold symmetry present, we should have phases of 0 and 180 degrees, and we can use this as an additional requirement for calculating our figure of merit scores on our amplitude and phase data, that being proximity to 0 or 180 degrees. Okay, systematic absences. So I mentioned with that aquaporin 1 crystal that there were a lot of spots missing, every odd spot in fact. And so basically systematic absences from our diffraction patterns or from our Fourier transform are something else which give us valuable information about the symmetry within our crystal. So systematic absences basically result from something called symmetry forbidden reflections. And there's two types of these. We have either axial or zonal systematic absences, which arise from glides and screws, and these basically result in a loss of odd reflections. Or we have integral systematic absences, which arise when a centre cell is chosen, and this generates twice as many theoretical reflections as what we would expect for the corresponding primitive cell. So just to highlight this, for the primitive cell, going back to OMP-G again, which conveniently has two glide planes located, you can see that what I've done here is taken our primitive cell and I've highlighted some key structural features within this OMP-G molecule just with some coloured dots. If we then translate those down to a 1D line, you can see that there's actually an internal periodicity within our primitive cell. So we've got this sequence of green, red, blue, blue, red, green, and then we go blue, red, red, blue, green. So you can see that there's an internal periodicity within there. The periodicity is represented by these two vectors here, and it's in the direction of B. And so what this means is that every second spot becomes symmetry forbidden because we've actually got effectively the periodicity is half the unit cell, and so we convert this to Fourier space, we get a reciprocity which is twice the unit cell. And so this is why every second spot is absent. The take-home message from this...
Just to make it, you say loss of odd reflections, but that's only on the main axis, right?
Yeah, that's right, yes.
Okay.
Yeah. Okay, so the take-home message from this basically is that systematic absences can be very valuable in identifying symmetry elements. Symmetry elements, symmetry elements. However, all space is a program which does not deal with systematic absences when identifying space groups. Now, I believe that the modified version of all space in the most recent version of 2DX does deal with systematic absences. Is that right, Henry?
Not all space, no.
Not all space, okay. So it still doesn't, sorry about that. But basically, when all space goes searching an amplitude and phase data for systematic absences, it doesn't take, for space group definition, it doesn't take into account systematic absences. And this is something you have to be very careful of, because what it can do is it can introduce incorrect symmetry into your calculations by trying to infer symmetry from spots which really aren't there. If there's a systematic absence, you don't have any data there, but all space, for example, may box out that area of the spot and use a very noisy area to calculate the amplitude and phase. And if you're unlucky, then this could have symmetric correlation, and you could end up with the wrong space group. So basically, the take-home message is that if you identify systematic absences within your diffraction pattern, within your Fourier transform, you should probably use this to try and narrow down the space group that you might have for your unit cell. And if you get something that's not consistent with a systematic absence, then maybe you need to look at your data more carefully and make sure that you've actually got the right space group. Okay, so while I'm talking about all space, and I've only got a couple more slides to go, while I'm talking about all space, anyone that's used this program before will find that you get 21 space group definitions when you search all space. And so these are shown on the left-hand side here. But as I've just said, there are only 17 plane groups, 17 2D space groups to be searched. So why do we search 21 different space groups with all space? And the reason for this is that there are a number of space groups, 4 of them in fact, whereby the decision of which axis is A and which axis is B in our unit cell is critical to the positioning of the symmetry elements. If we've only got one mirror plane, for example, present, and that would be the case in the P12 crystal form, which only has one mirror plane present, then choosing the A star or the B star, the position of the A star or the B star vector is quite important to the relative positioning of that mirror plane. And if we get it back to front, then what happens is we basically get a different symmetry definition, which is covered by these two different P12 forms. And so basically all this means is that if you get P12A instead of P12B, you just need to flip your axes to get back to the CCP4 convention. Yes, Brian?
I was wondering if you could just comment on that CCP4 convention, because we get a lot of emails from people who are wondering about how to label their axes canonically such that they work with.
Yeah, off the top of my head, no, but yeah, basically CCP4, but you would need to go into the headers of CCP4 and all the data is included in there, but the CCP4 conventions and the MRC conventions do differ somewhat in terms of where they position their axes in defining their space groups, and that basically stems from the fact that CCP4 is driven by the original 3D space groups, and for some axes, for some definitions which they may call P2, they may have the two-fold in X, for example, whereas we would have the two-fold in Z because that's the only place we can have it in a 2D crystal. But yeah, there are inconsistencies with the two definitions, and if you're concerned about that, you should definitely go into headers and have a look. Okay, and I think this is my last slide. So just some other considerations for the symmetrical averaging of data. So as I mentioned, up front, the plane groups describe the symmetry of untilted crystal specimens. And basically, as soon as you tilt the crystal specimen, then this symmetry is lost. Usually going to a tilt of 2 degrees or more will completely abolish symmetry within your crystal image. So in order to determine the space group of your crystal, this may seem obvious, but you need to have a truly untilted crystal specimen. Otherwise, you're not going to identify that symmetry. Similarly, it's important to work with astigmatic images when trying to, with non-astigmatic images rather, when trying to identify the space group. Astigmatism causes a non-uniform effect of the CTF on your amplitude and phase data, and once this non-uniform effect is introduced to symmetry-related spots, then the symmetry between them will be lost. And so again, you'll have a hard time trying to identify the true symmetry of the map. As Brian mentioned earlier, these symmetry rules obviously only hold when data is shifted to the crystallographic phase origin. And so again, when Allspace searches the symmetry group definitions, what it does is it shifts stepwise all of your data, evaluating the phase origin at the same time as evaluating the space group definitions. Another important point to make is that stain exclusion patterns caused by negative stain can sometimes introduce symmetry artifacts. And so oftentimes it's best to evaluate the symmetry of your space group with a cryo sample, even if you can only acquire one cryo sample. Yeah?
So you say negative stain can cause overestimation of symmetry. I think it's actually the other way around. Because if you have opposite orientations of the proteins in the membrane, you get different staining of the lower and the upper side. And so it looks as if they are different.
Sure, yeah.
So I think it's the other way around, you get underestimation of the symmetry.
Yeah, probably. Yeah, in that case, yeah. So okay, so we'll just say that it can cause inaccurate symmetry estimation. But I guess the test is that when looking at symmetries, you should look in cryo. You should evaluate your data in cryo, but you should also check for the presence of subsymmetry. So if, for example, you've got P6 symmetry within your crystal, you should also get a tick in the box of P3 and a tick in the box of P2. And if you don't, then maybe that would suggest that you've got some sort of stain artifact or something like that, which is giving you a crystal symmetry which is not actually present within your data. And you should only ever apply the symmetry when it's consistent in all images and when all the subsymmetries are consistent. Okay, so this is basically just a list of references for some of the structures that I've put up in there and also some other further reading. And that's basically all I had to say today. So if there's any questions, I'll take them. Otherwise, I'll just move on to the next talk.